In this video, we will do a couple more examples of solving a system of linear equations by elimination. These will be slightly more complicated than the example in the last video. So I hope that you will find them really useful as you learn and develop this skill. So sometimes we have to multiply both equations by a constant in order to eliminate a variable. So if we were to do the same kind of variable comparison that we did last time with our coefficients, we could see, let me change back to a pen. Sometimes I think faster than my computer will let me change tools. So computer, what's going on? There we go. All right, so here we have 2 and 3. Neither is a multiple of the other. And over here, we have 5 and 3. Neither is a multiple of the other. So what we have to do is find their least common multiple. So the least common multiple is the smallest number that can be divided by each factor. If we were to do the prime factors of a number, then the least common multiple would be simply all of the factors that appear the smallest number of times they each appear. And as I'm saying that, I'm realizing it sounds a lot more complicated. So I will probably do an example of least common multiples later on near the end of this video. But for the meantime, I want us to get through the bulk of this example. So the least common multiple, the LCM of 2 and 3 is 6. The LCM of 5 and 3 is 15. I like to keep, and I encourage others to keep their numbers small whenever possible. So when I have an option between 6 or 15, I'm going to go with 6 because that will allow me to keep my numbers smaller, and so the computations will be easier. So I'm going to, let's pick a new color. I like colors. All right, so I am going to do 3 times equation 1 and in fact, rather than writing that number sign, I am going to do 3 times E1, E for equation, and then E2 for our second equation. Since both terms are positive, I will need to multiply the second one by a negative number. So 3 times E1 minus 2 times E2 is the new equation that I'm going to make. And so I have 3 and 2. And so right now what I'm doing is just to help keep myself organized. I'm breaking it down into more steps. So I'm going to put our first equation up here, and then our second equation right here. Whoops, too far. Okay. And then I'm going to actually distribute. So 3 times 2x is 6x. 3 times 5y is going to be 15y. And then 3 times 11 is 33. Negative 2 times 3 is negative 6x. Negative 2 times 3, y is negative 6y. Rather than writing plus negative 6y, I can just write minus 6y. And then again, negative 2 times 3 is negative 6. And I'm adding all of these terms, so I can put that plus sign out here. So adding up 6x and negative 6x, these terms just cancel out, so I don't need to write anything down here. 15y minus 6y is going to be positive 9y. And then 3y, that is not 3y, 33 minus 6 is going to be 27. So our new system I want to keep, I could honestly keep either equation. I want to keep the one that has the smaller coefficient because I like to have smaller numbers to work with. So our first equation, E1, isn't going to change. It's still going to be 2x plus 5y equals 11. And then our second equation, I'm going to call it E2.2 because it's the second version of our second equation. And this is just 9y equals 27. Now, because we have one of our equations reduced to only a single variable, we can simplify that equation even further. So over here, I'm going to show that we can divide 27 and 9 both by 9. So we get y is equal to 3. And so in this sense, we get a new system. We could plug 3 into the other equation, but I want to show you how we can continue to eliminate variables, since that will mirror what's going to happen with matrices. So we have our first equation still unchanged, and then our second equation, I'm going to call it 2.3. And so that's 2x plus 5y equals 1, and then y equals 3. And I want to get rid of the y term from our first equation. And to do that, I'm going to do equation 1 minus 5 times equation 2.3. 5 times equation 2.3, or negative 5, excuse me, will allow us to cancel it out. So we'll have 2x plus 5y equals 1. This is equation 1. And then I'm going to multiply equation 2 by that negative 5. So we'll have negative 5 times y is equal to negative 15. And then we're adding, so we have 2x, positive 5y and negative 5y cancel out. So we have nothing here. And then 1 minus 15 is going to be negative 14. And then we can take a step further and in fact divide both sides by 2, which gives us the equation x is equal to negative 7. So in a sense, we have now finished our question because we have solved for what y and x are both equal to. But I want to show you what this looks like if we write it as let's call this our system, and I'm going to put final in parentheses. So we have the second version of our first equation, which is x equals negative 7. And then we have the third form of our second equation still, which was y is equal to 3. You'll notice that I left blank spaces so that the variables still line up vertically. This will make more sense why it's useful when we start writing matrices. But this final system is our solution. If we wanted to write our solution as a coordinate point, we could say negative 7, comma 3, since this would be a coordinate point. So solving systems of equations, they can be overwhelming because there's a lot of little steps. But if you really break it down piece by piece, a lot of these skills are skills that you have developed and practiced over years of studying math, like the least common multiple, distributing a constant over multiple terms, adding like terms, dividing to solve an equation, repeating those steps with different numbers. All of these are small skills that we are combining into a larger toolbox that allows us to solve these systems. I will do one more example, but to wrap up this video, I want to add a little bit about least common multiples, because that is an important topic. So least common multiples. So it can be helpful when we're thinking of least common multiples to recall our prime factorization. So every number has exactly one prime factorization. It is called the fundamental theorem of arithmetic for those who go on to study number theory. And it might not feel all that exciting, but it's actually an incredibly profound math fact. So a prime number, so prime numbers have exactly 2 factors, which is the number 1 and itself. So examples of prime numbers are 2, 3, 5, 7, 11, and so on. However, not 12, because 12 can be expressed as 3 times 4, which means it has factors other than itself and 1. And then there's a big question, is 1 prime? For the longest time, no, I'm not going to tell that story. I want you to think about this. It is a fun exercise. You can apply this definition and determine for yourself if 1 is prime. The word exactly here is really important. But I also want to find what we mean by factorization. So a factorization is a list of all factors. And a factor is something, generally a number, being, my handwriting suddenly got really bad. Let's try this again. Okay, so a factor is a number being multiplied. Multiplied, I think I was misspelling it. Okay, and of course, factors, when we multiply, give us products. An addition would give us a sum, good, important vocabulary terms. So what we're saying, the prime factorization of a number is the list of all of the prime numbers that multiply to the number itself. So let's come back to this example of 12. 12 is not prime. We would call it a composite number because it's composed of primes. So 12, we can think of as 3 times 4. And then 4 is 2 times 2. So the prime factorization of 12 is 2 times 2 times 3. If we want to get really fancy, we could write it as 2 squared times 3, but this middle form is sufficient. Let's look at, how about 45? Well, 45 is 9 times 5, if I'm not mistaken. And 9 is 3 times 3. So the prime factorization of 45 is 3 times 3 times 5. And so now that we have 2 examples, we can come back to our conversation about least common multiples. So what is the least common multiple of 12 and 45? And the comment I made earlier uses the prime factorizations. So 12, I'm going to draw a line here. So we have 12 and 45. The prime factors of 12 are 2 times 2 times 3. And now I'm going to write the prime factors of 45, and I'm going to line up all of the numbers that are the same. So notice that they both have a 3. So when I write the prime factors of 45, one of our 3's is going to be stacked on top of each other. So we'll have 3 times 3 times 5. If there were more numbers in common, I would just stack them as well. And so the least common multiple is if we take all of these numbers, so 2 times 2 times 3 times 3 times 5, and we multiply all of these together, we'll get the least common multiple. So that would be, this gives us 4, this is 9. Let's see, 9 and 5 is 45. And then 4 times 45, that's like, some mental math, it's like 4 times 50, but then I have to subtract 4 times 5, which is the difference between 50 and 45. So that would be 200 minus 20. So altogether, that would be 180. In order to get 180, so let me pick a new color. There we go. In order to get 180, I need to multiply by the missing factors. So 45 needs to get multiplied by 2 times 2, and then it'll give us 180. And 12 needs to get multiplied by 3 and 5, the missing factors, and then we'll get up to 180. So this would be how we can use our least common multiples to find ways to cancel out terms when solving equations by elimination. And of course, if you would much rather plug this into a calculator rather than using mental arithmetic, that's totally fine. I still recommend checking your work with a calculator, even if you use mental arithmetic. There have been plenty of times when I have made a mistake and I've had students say like, hey, shouldn't that be this number? And I'm like, yep, it should be. I wasn't paying attention. I made a mistake. Thank you for helping me fix it. So I feel like there's one other thing that I'd wanted to say about least common multiples, but yes, I do remember. So the first way I described a least common multiple was all of the prime factors, the smallest number of times they appear. So what that means, actually that, now having said that again, that's actually wrong. It's the largest number of times they appear. So we have 2 2s, we have 2 3s, that's the largest number of times that they appear in either number, and then 1 5. If I went with the smallest number of times, we would get a different number. So that would be, would that be the greatest common factor? Or would it be unrelated? That's a fantastic question that I'm going to leave to you as an exercise. Point being, moral of the story, if you can find the least common multiple of 2 numbers, you are equipped to use that to solve systems of equations when there are no common, when one coefficient is not a multiple of the other.